We are now going to study the third of our series of the charts most commonly used in aviation, the polar stereographic projection. As before, we start with the reduced Earth. We add a light source. Note that, for this projection, the light source is at one of the poles, not the centre. A sheet of flat paper representing a plane surface is placed at the other pole, exactly perpendicular to the Earth's axis, and the light is projected. You can see that point A has an image at A1, point B at B1, and so on. The result looks like this. The scale is correct near the pole, but expands as we move away. This projection is used to create the polar stereographic chart. Of the charts that we consider, this is the only perspective projection. It is exactly as the light falls. By choosing the opposite pole instead of the centre of the Earth for the light source, we have produced a projection that is already orthomorphic, and so there is no need for any mathematical adjustment. This diagram is based on having the light at the South Pole. It shows the geometry of how the projection is generated. You can see that meridians, which appear on the globe like this, will appear on the chart like this. The parallels will be concentric circles. However, they are not evenly spaced. The chart distance between equal changes of latitude is expanding as we move away from the pole. We can arrive at an equation for the rate of scale change, but in order to do so, we first need to introduce the idea of the co-latitude. We know that latitude is the angle measured from the equator in the direction of the pole. Co-latitude is the angle measured from the pole towards the equator. Latitude and co-latitude must add up to 90 degrees. So that if the latitude were, say, 60 degrees, the co-latitude would be 30 degrees. Now consider the two light paths shown in the diagram. Let's take the one which passes through the equator. If the latitude is 0, then the co-latitude is 90 degrees. Now let's look at the angle that the light path makes with the Earth's axis. From the pole to the centre of the Earth is 1 Earth radius. And from the centre of the Earth to the equator is also 1 Earth radius. So we have an isosceles triangle, with the angle that the light path makes with the Earth's axis having a value of 45 degrees. The angle that the light path makes with the Earth's axis is always half the co-latitude. This is a general result and is true for any co-latitude. For instance, if the co-latitude is 30 degrees, the angle that the light path makes with the Earth's axis will be 15 degrees. The scale expansion along the sheet of paper is therefore a function of the co-latitude. You are not required to remember the details of the above explanation, but you should remember the equation that results, which is that scale expands away from the pole at a rate of the secant squared of half the co-latitude. The result is a projection in which the distance between concentric circles of latitude is expanding as we move away from the pole. The projection can be used to show all of one hemisphere, as here, where you can see the equator. In fact, it would have been possible to extend the coverage 10 degrees further south, taking in some of the southern hemisphere, and the chart is still fairly undistorted and usable. This makes the polar stereographic a very good strategic planning chart on a global scale. We're now going to consider all the important chart properties in the way that we did for our previous charts. This is our list, and we'll go through them one by one. The first of these is scale. The scale is correct at the pole, where the paper touches the reduced Earth. Elsewhere, it expands as the secant squared of half the co-latitude. The equation for scale is that scale at any latitude equals the scale at the pole times the secant squared of half the co-latitude. We will now show how this equation works by calculating how the scale changes between the pole and 78 north. This is to show a worked example of the calculation, although, as we shall see, 78 north also has a particular significance. We should emphasize that these calculations are not required by the examination syllabus. This is simply a demonstration. If the latitude is 78 north, what is the co-latitude? If the latitude is 78 north, the co-latitude will be 12 degrees. So half the co-latitude will be 6 degrees. Let's substitute it into the equation. Secant squared 6 degrees is just another way of saying the secant of 6 degrees times the secant of 6 degrees. And, as we know, secant is 1 over cosine, so we can substitute in order to have the number 1 as the numerator. Let's assume the scale at the pole to be 1 to 1 million. We can look up the cosine of 6 degrees on our calculators. Rounded to 4 figures, it's 0.9945. And if you now multiply out the right-hand side, you'll find that you get a scale of near enough 1 to 990,000. A scale of 1 to 990,000 is within 1% of our original scale at the pole of 1 to 1 million. So, between latitudes 90 and 78, the scale is within 1% of the scale at the pole, which we take to be a constant scale chart. A similar substitution can be carried out for a latitude of 70 degrees. Out to this latitude, the scale is within 3% of the scale at the pole. This constancy of scale makes the polar stereographic projection an almost ideal map for flying in polar regions. Polar routes have become much more common now than previously because of 3 recent developments. Firstly, there is the breakdown of former political rivalries, with greater freedom of overflying rights. Secondly, there is the advent of aircraft of long range and endurance and their associated ETOPS regulatory procedures. And thirdly, there is very wide availability of flight management computers based on inertial navigation systems. It has now become common to use polar routes, which are often shorter, and some go very close to the pole indeed. Imagine a route like this, which is typical. Take the 1% scale zone. The co-latitude of 78 north is 12 degrees. There are 60 nautical miles to a degree, so the distance from the pole to latitude 78 north is 720 nautical miles. If the aircraft is entering on one side and leaving more or less on the opposite side of the circle, The total distance in the 1% zone is around 1400 nautical miles. At typical jetliner speeds of around 450 knots TAS, that is approximately 3 hours flying time. A chart which can be considered constant scale and allows measurement of distance with a ruler for over 3 hours flying is a very useful projection. If the 3% zone is taken, the same chart can be used for 5 hours.